The agenda for today is we're going to look at a two-sample t-test with equal variances and unequal ends per group. We're going to set up the hypothesis test. We're going to look at the distribution of the test statistic under the null and alternative, and calculating power and sample size under the alternative. And then we're going to illustrate this in R. To set it up, we need two populations, both normal, mean mu1, mu2, different sample sizes, N1 and N2. And you can kind of see that. The sample sizes are different, sample means, pooled variance, significance level alpha, and here's the standard test statistic. We're going to test, are the means equal or are they different? And under the null hypothesis that the means are the same, this is a central t distribution with n1 plus n2 minus 2 degrees of freedom. Under the alternative, it becomes a non-central t distribution with the same degrees of freedom, but non-centrality parameter of this, the product of the ends divided by the addition of the ends, the difference of the means over sigma. So when we calculate power, and that means the alternative is true, if we're given the sample size and the means and the population standard deviation and the value of the test statistic, calculating power is straightforward. But it is not straightforward when we want to calculate sample size. So we're given power of, say, 80%, and then we want to increase the sample size, the samples, until we achieve 80% power. But how do we do it? Do we increase both of them together? Well, that was a video I did earlier where the sample sizes were equal between the groups. Here we're assuming they're not equal. So maybe we want a 1-to-2 ratio or a 1-to-3 ratio. And this is one approach how to do it. We're going to let the sample size for population 1 be K1 times N, and the sample size for the second population in 2 is K2 times N, where N goes from 1, 2, 3, etc., and the K's are integers. Now, let's set this to be K1 is 1 and K2 is 3. So it's a 1-to-3 randomization ratio. And then we're going to increase the sample size in it like this. So when it's 1, this is 1 and 3. When N is 2, this is 2 and 6. 3 is going to be 3 and 9. And so we maintain the 1-to-3 ratio that we set by picking the K1 and K2 values. And it can be shown that this is the non-centrality parameter when we do that. Okay, and now I'm going to illustrate this within R. So here I'm using R on an Ubuntu Linux machine, and we're going to look at the two-sample t-test with equal variance and unequal ends per group. The hypothesis test, are the means equal or are they different? Significance level alpha. Now to illustrate this, we need to pick sample sizes and an alpha. So let's pick an alpha of 0.05, sample sizes of 20 and 30, which they're unequal. And let's create some data and then plot our t-test. So here, this is the central t test, and we need to find the rejection regions. So we'll shade those. And since this is a two-tailed alpha 0.05, each area here is 0.025, or alpha divided by 2. And when we calculate a test statistic, we see if it falls in the rejection region, we reject that null hypothesis. If it doesn't, then we don't reject the null hypothesis. But here we're looking at how to calculate power and sample size. Now to calculate power and sample size, we have to assume that the alternative is true. That means pick values for mu1 and mu2 so they're not equal. And so here we're going to pick a value of 3 and 2. We also need to pick the common standard deviation between the two distributions. We'll store those values in M1 and M2 and sig. And then let's plot that distribution. So since we're under the null hypothesis, meaning it's true, this is the distribution we get. And then to calculate power, that means the probability that we reject, given that this distribution is the true distribution. So let's shade the region here. So power is this green region. And notice that there's some here because the rejection region starts there and goes this way, and there's a little bit of area under the curve on both sides. Now, to calculate power using R, the base R, you can't, because there's not, well, with a built-in function you can't, because there you assume that the sample sizes are equal in that power.t.test function. So you can't use it. And there is a package called PWR where they look at power, and you can have unequal sample sizes, and it'll calculate power in those settings. But here, let's just calculate it from first principles. So we calculate the area to the right here, and it's 13.3%. Then let's calculate the little left tail, which is 0.2%, so very small. Add them together, and then this is power under this setting. So let's find the needed sample sizes here. And again, base R doesn't have a function that does this. Now, the PWR package, it allows you to have one unknown. So you can choose a sample size for one of the samples, and then it'll find the needed sample of the other, and or vice versa. But it won't search them together. And this is a way to do it from first principles, that we can search them together. And we're going to let N1 equal K1 times N and N2 K2 times N. And the reason we do this is that we can let these parameters be any number we want. So here we're going to let them be 1 and 3. So this is a 1 to 3 randomization. We could pick 1 and 2 for a 1 to 2 randomization, or we could even pick 1 and 1 for the equal sample size. But that's already been covered. So let's pick a 1 and 3. And let's pick N equal 20, which makes our sample sizes 20 and 60. And let's calculate power. So the power in this setting is 15.9%, okay, which is not 80%. So what we could do is go back in here and switch that to 21, recalculate power, and if it's not enough, switch it to 22, and we just keep doing this until we achieve the power we want. Well, that'll take time. So let's write a while loop. And it means while the power is less than 0.8, keep incrementing the sample size by 1. And then stop when you're done. So let's do that. And it's already cycled through it. And the sample sizes that we need to achieve 80% power are 168 and 504, which is a 1 to 3 ratio like we wanted. So now, to illustrate that this does work, we are going to recalculate this in a 1 to 1 ratio. So now this is the equal sample size per group setting, which R does have a built-in function for that. So here it says we need 253 observations per arm to achieve an 80% power. So now to do this in R, we leave N blank because this is the N per group, and the same delta and sigma and significance level, 80% power, and we calculate it. And it says that we need 253 subjects to achieve this power. So what does the distribution look like in this case? Oh. So I need to put this up here. So So I want to put 253 observations in each N1 and N2, and then I want to plot the distribution. I want to plot the alternative distribution, well, assuming it's true, and let's shade the area to see what we're doing. And so in this setting with 253 subjects per arm, this is the null distribution, this is the alternative, and this is a rejection region, and so there's 80% area here. And notice that it tried to, there's a little green line, I'm not sure if you'll be able to pick that up, it tried to calculate power over there too, which is essentially 0. So I hope that you enjoyed the video, and I will talk with you later.